polynomials in this unit. So we graph polynomials by graphing zeros and end behavior. Then the next time we did division with long and synthetic division. We're going to be using long and synthetic division, mostly just synthetic today, a lot. So hopefully that made sense to you. So what we're going to be able to do today is we're going to be able to identify possible rational roots of a polynomial, and then you'll be able to also use Descartes' rule of signs to determine possible positive and negative roots, and then also you can find all the roots of a polynomial. So first of all, the big thing is when I say something, you know what I'm talking about. So let's do some vocabulary checks to make sure when I say something, I think that's what's confusing for people. They don't understand what I'm saying. So everybody listen. We know roots are the zeros, x-intercepts, or solutions of a polynomial. Correct, everybody. Zeros is just another word. Yeah. Just drop those off. Yes, perfect. That's all I need really from you today. Now, rational means it can be written as a whole number or fraction. That's by definition what a rational is, a whole number or fraction. So what we're doing today is we're focusing on rational roots. So that means that we would be focusing on zeros or solutions that are whole numbers or fractions only. Does everybody see what I'm saying? Rational roots. Whole numbers or fractions only. That's kind of our focus today. Now, this is an idea we learned in secondary 3. We're just going to be adding on to it a little bit more advancedly. So let's decide here. I've listed out some roots, some different types of roots, and you need to be able to tell me, are they rational or irrational or imaginary? Because today we're dealing with rational roots only. So is x equals 1 rational? A rational root? Yes, a whole number. Is root 2 a rational root? No, because the square root, this square root of 2 cannot be technically written as a fraction. If you were to type it into your calculator and hit math, enter, it's a really long decimal. It can't be rewritten as a fraction, whole number or fractions. So this is an irrational root. Right, here's an imaginary root, correct? This is another irrational root. Now, these, rational root, rational root, rational root. So rational roots are roots that can be written as fractions or whole numbers. Now, think about it. These type of roots come from the quadratic formula, if you think about it. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So just keep that in mind. So we're learning, the first thing we're learning, and we're going to be using it pretty much the whole lesson, is called the rational root theorem. So what the rational root theorem does is it gives us an exact number of possible rational roots for every polynomial, which makes it really nice because we're able to look at a polynomial and see the only possible whole number or fractional solutions of it. Does that make sense? Okay, so it says right here, we can find the possible rational roots of a polynomial that has integer coefficients, so that means whole number coefficients, by doing all possible p's divided by q's, where p is the constant coefficient or its factors, and q is the leading coefficient or its factors. So everybody, this is something you'll just kind of have to remember. So here is my polynomial, x cubed minus 3x plus 2. Our q is always going to be the leading coefficient here. So our q is 1, and our p is going to always be the constant. So it's plus positive 2. So what I've done is I've listed out all the factors of p. So let's look at 2. Listing out all the factors of 2. That means what multiplies to be 2. Now, we don't know if it's positive or negative, so we do plus or minus 1 is a factor of 2, plus or minus 2. Do you see how 1 and 2 are the only factors of 2? And then my factors of q. So factors of 1 are just plus and minus 1. So now this gives us, for this polynomial, the only possible fractional whole number roots that this polynomial could possibly contain. So what you'll do is do p over q. All possible p over q's. So look what I did. 1 divided by 1 is 1. You guys see how I have 1 as a p over q? Now I did 2 divided by 1, because we're doing all p's divided by all the q's. 2 divided by 1 is 2. So the possible p over q's are 1, negative 1, 2, negative 2. Does everybody see? So look how nice this is. We know that if this polynomial has fraction or whole number roots, it will be contained in this list. It's one of those, and only those. It couldn't be anything else. There is no possible way that 3 is a solution. Does everybody see how that makes it kind of nice? Now, question for you, how many roots, how many solutions does this have? 3. actually its own theorem. It's called the fundamental theorem of algebra. If it's degree 3, there are 3 solutions. Now keep in mind, everybody, just because we have 3 solutions doesn't mean it's going to be 3 of these, right? Because think about it, aren't there imaginary roots? Aren't there irrational roots? So it's not necessarily these. Does that make sense? These are just the possible whole number or fractional roots. Okay, so it just kind of helps us. Okay, so we just did this one. So this is just kind of your thought process, everybody. But this time we'll actually go through and find the actual rational roots. So what it says is find all possible rational roots and state which ones are actually rational roots. So we always do our P over Q. Now, what comes first? This would be our Q, this would be our P. Now that kind of goes backwards because we do P over Q, so a lot of times people go PQ because it just feels natural, but it's backwards, so just keep that in mind. So factors of P were plus and minus 1, plus and minus 2. Do you agree that those are the only factors of P? This is the same one we just did, I'm just showing it again. My Q is 1, so the only factors of 1 are plus or minus 1. So then our P over Q would be 1 divided by 1, that's why I got 1, plus or minus 1, 2 divided by 1, plus or minus 2. So 1, negative 1, 2, and negative 2 are the only possible whole number or fractional roots. So now here's how we can test. Well, actually, you tell me. Any ideas of how we can test? Is 1 a root? What did we talk about last time in the last lesson? Synthetic division, and what would happen if it was a root? The remainder would be 0. Does everybody see? It's just a way of guessing and checking, and then we are checking for sure. So now we'll do 1. So let's put in our coefficients. 1, don't forget x squared is not there, so 0. Negative 3, 2. So we add straight down, multiply up, add straight down, multiply up, add straight down, multiply up, add straight down, 0. Does everybody see how now I know for sure 1 is a solution? So I make a bucket of solutions, I'm going to call it, just so I can put my final answer somewhere. We know x equals positive 1 definitely worked since my remainder was 0. Now there's a couple different ways to continue from here. Everybody listen, this is really important. So we could keep testing values. We could now do negative 1. We could do 2. We could do negative 1. Do you guys see what I'm saying? I mean, sorry. Yeah. Oh, I wrote negative 1, but didn't I meant to write negative 2 right here. So I could keep testing, but there's a smarter, more efficient way that's quicker, honestly. So everybody look, we went from degree 3, we divided it once, and it worked. Wouldn't that make this degree 2? So what I would do is say, okay, since I'm down to a quadratic, x squared plus x minus 2, to find the other rational roots, I'm going to solve by factoring, so I don't have to keep testing. Now, what if this quadratic did not factor? To continue solving, I would need quadratic formula, which gives us imaginary and irrational roots. So if this quadratic didn't factor, wouldn't we know for a fact this is our only rational root? Yes, otherwise the other 2 roots would be imaginary or irrational if we need the quadratic formula. Does that make sense? So it wants only rational roots, so let's see if it factors. If it does, guys, if it factors, it's going to factor to be whole number or fractional roots. So let's go ahead and see. Well, multiplies to be negative 2 and adds up to be 1. 1 times 2, negative 1. We can quick factor. So it quick factors to be x minus 1, x plus 2. So what are my other 2 solutions? 1, so didn't we already list 1 time? Well, we just got it again, so that'd be multiplicity of 2. And also x equals negative 2, which was a possibility, so we know we did it right. Now count, I have degree 3 and I have 3 solutions, so it's all making sense here. So this one did happen to have 3 rational roots. Any questions on that? See, it's just a memorize it. It's pretty easy, but we lucked out. The thing is we lucked out and got the right one on the first try. That won't always happen. That's what makes it a little bit more of a problem. Okay, let's do another one. Okay, it says find possible rational roots and then state which ones are actual rational roots. And then it wants us to factor it completely. Okay, we can do that. So what we would do is say, okay, first of all, if you look at this, we would be able to look and say, could we factor this by any technique that we've learned so far? Yeah, and we would try grouping, and then we'd pull out an x squared, wouldn't we? Left would be 2x plus 1, and then do you see how we can't factor anything out of this? So grouping doesn't work, and that's why we're having to use P over Q. Do you guys see? So just keeping in mind. Okay, so Q comes first, P is last. So then I go up to the side and list out all the factors of P. I go in order. So factors of 6, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Agree? Now factors of Q. Factors of Q would be plus or minus 1, plus or minus 2. So now what I'm going to do is list out all possible P divided by Q's, because these are the possible fraction or whole number roots that that polynomial could contain. 1 divided by 1 is 1. 1 divided by 2 is 1/2. 2 divided by 1 is 2. 2 divided by 2 is 1. You don't need to list it again. We've already got that one. See, I'm doing all the possible P divided by Q's. 3 divided by 1 is 3. 3 divided by 2 is 3/2. 6 divided by 1 is 6. 6 divided by 2 is 3. We've already listed that. So if this is going to have whole number or fractional solutions, it's in this list for sure. But notice there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 values. You guys see how this is a little bit more complicated? Okay, so we're going to have to just kind of roll with it and start testing things until we find something. Now, once again, isn't it degree 3? So once we find 1, we'll have a quadratic, and we'll continue by factoring, or if we need a quadratic formula, we'll be done. Okay, so everybody, let's split up so we can kind of get through this quicker. Let's start with the whole numbers maybe. So I'm going to take 1, somebody else take -1, somebody else take 2, somebody else take -2, somebody take 3, -3. Everybody pick a different one, 6, -6, and then you can say, Ms. Christensen, 3 works, or whatever. Does that make sense? I'll take 1, the easy one, of course. So go start doing synthetic division with this coefficient, and if the remainder comes out 0, then we know it's a solution. Okay, so I'm going to put an x does not equal 2 here, so we know 2's out. I see my remainder with 1 is -4, so x cannot equal 1 for sure. It's not plus or minus 6. Two is a solution. Okay. So somebody else says 2 is a solution, so let's go through and see if that worked. So do you guys see on the test, though, you're not going to have people helping you out, you're just going to have to plow through. Do you get what I'm saying? Just keep testing them by yourself. Okay. So 2, we put in our coefficients. 2, 1, -13, 6. So we add straight down, multiply up, add straight down, multiply up, add straight down, multiply up, add straight down, 0. Perfect. So I'm going to make my bucket of official rational roots. So x equals 2 worked. Now from there, because we went from degree 3 down to degree 2, we're going to not keep testing values. Instead, we're going to look at our quadratic and do it that way. So this is a 2x squared plus 5x minus 3. And now I'll solve for the other two roots by factoring if possible. So what multiplies to be -6 and adds up to be 5. 3 times 2, 1 times 6, which one will work? 6 and 1, so one of them would have to be negative. This one? It's a long factor though, so let's give myself some room. So we drop and break. So we drop down 2x squared, drop down -3. Breaking down 5x as minus x and plus 6x, factoring by grouping. Pulling out the greatest thing in common is x, left is 2x minus 1. Right here I'm pulling out a 3, positive 3, left is 2x minus 1. Now I can pull out a 2x minus 1, so it divides out, leaving me with x plus 3. Because it factored, I'm keeping going. If it didn't factor, I'd need quadratic formula. And in this lesson, we're only doing rational roots. I can't stress that enough, so you'd be done. Does that make sense? Okay, but so what's my other two solutions? 1/2 and -3, were those possibilities? Yes. Questions on that? Yes. Yeah, but that would have taken longer, and we're trying to learn some techniques to make our life not so miserable. Yeah. Good question, though. Yes, you could have tested all of them until you saw that those 3 would have been the only ones with the remainder of 0. Okay, so... Okay, I want to come back to this one, actually, but don't let me forget to come back to it. There's a reason I want to come back to it. I think you need to see... I'm trying to figure out the best example to go to next. It was kind of hard for early morning, so I'm trying to remember what... Okay, this one. Okay, everybody write this one down. It says factor, oh crap, we didn't go, I need to go in a minute. It said to factor it, but we didn't factor it, but the other one said to factor it completely. So we'll go back to it in a second. Okay, write this down. It just says factor the polynomial completely. So notice if you look at this, we don't know any factoring techniques to factor this. So we're going to have to solve it and then work backwards. Now notice it's degree 5. How many solutions will I have? 5. Guys, if it's degree 5, you'll have 5 solutions, right? Therefore, there'll be 5 factors. We got to go through and find them all. Now, because we don't know any factoring techniques, that's why we've learned now P over Q. It's another technique to factor something. It's our least favorite, but it is what it is. Okay, so what we would do is say our Q is our leading coefficient. Our P is our constant coefficient. Let's list out factors of P. Plus or minus 1, plus or minus 3, plus or minus 9. Factors of Q, plus or minus 1, plus or minus 2. So now P over Q. 1 divided by 1, 1 divided by 2. 3 divided by 1, 3 divided by 2. 9 divided by 1, 9 divided by 2. Okay. Now here's what I want to point out to you. It's degree 5, so we're going to want to, each time when we divide it, we're going to want to get it lower and lower down to until it's quadratic. Does that make sense? So then we can continue solving the easy way. So every time we divide it, it's going to get smaller and smaller. Okay, so let's start testing. Once again, everybody be really careful. Pick one and test it, and then tell me yes or no when you get it. When you get one that works. I'll take 1 again. So don't take 1 because I'm doing 1. Oh, I just found one. Sweet. Okay, no one keep testing. No one keep testing. No one keep testing. There's a reason. No one keep testing. I just found one. I don't want you to keep testing for a reason. Okay. So, not that yours wouldn't still work, but I just want to make a point here. Okay, so everybody look. I went through and did 1, and do you see how it works? So what you would do is when you find the first one, you're going to stop for a second. Let's go make our bucket of solutions. So x equals 1 worked. There's a reason I had you stop. Here's what you're not going to want to do. You are not going to want to go back to the original and keep testing. Because then if you find another one, you'll only be down to degree 4. Well, aren't we down to degree 4 right here? Well, I would rather then take this new polynomial, which is degree 5 divided by degree 1, and we get degree 4th. So this is 2x to the 4th plus 7x cubed minus x squared minus 15x minus 9. Here's my new polynomial. Do you see how it's smaller? Degree 4. We're going to want to now test with this polynomial. Notice it will have the same rational roots. Do you see how 9 and 2? 9 and 2? they'll contain the same rational root. It's just now, if we find another one, won't we be down to degree 3? You guys see what I'm saying? So then it's smaller and smaller each time we find one. We're going to want to use the new coefficients each time so we can continue to get smaller and smaller. Does that make sense to everybody? Okay. So now instead, sorry, I didn't mean to be like, stop, but there's a reason. So did anybody find another one that did work where you threw it? Negative 3. So let's just pretend like we didn't know. We would have these coefficients and then we'd keep testing values. So we're trying negative 3. We're just happening to try negative 3. So we'd put in 2, 7, negative 1, negative 15, and negative 9. And if it worked up here, it'll work down here. So now from here, I'm going to add straight down, multiply up. Here we go. Come on, computer. Okay. Add straight down, multiply up. Boom. So negative 3 works. So going to my list here, x equals negative 3. Okay, so now we went from degree 4 to degree 3. I would write it down each time I write it down, and then I look to see if there's a factoring technique I can use to continue solving instead of having to keep testing p over q. So now we have 2x cubed plus x squared minus 4x minus 3 equals 0. Now from here, I always check, would it work if I see 1, 2, 3, 4 terms? Do you see how I have 4 terms? There's a lot of times you'll get to this point and it'll factor by grouping. And wouldn't you way rather solve by factoring by grouping than continuing to test the other 10 values? Yes. But this one doesn't factor by grouping. If I try, the safe haven's not the same. So unfortunately, we have no choice but to continue solving with p over q. Okay, so we would keep testing more out of this list here. Did anyone get another one that happened to work? It'll still contain the same zeros, but good question. We could redo p over q, but it will be contained in here, the same thing. I'm trying to think if that would be useful to us. It actually might eliminate, would it eliminate 9 and 9/2? Does everybody see what she's saying? If we redid p over q here, it would not have 9 or 9/2, and they should have the same zeros. So we can actually eliminate 9 and 9/2. So once again, but let's say you didn't know that, just keep testing. Like if you forgot that, you would just keep testing. You would get a remainder of not 0 if it didn't work. But you're making a good point, Chloe. So once again, here's my q, here's my p. So we have factors of 3 plus or minus 1, plus or minus 3, factors of q. You don't need to redo this every time. I'm just showing you plus or minus 1, plus or minus 2. So Chloe's saying, do you see how the 9 parts aren't there in my possibilities? Now, that means then that these won't be solutions, because it has to be solutions of each piece. Okay, so what's maybe another one we should test? We've already done negative 3. Negative 1 works? Okay, cool. So we would just happen to keep testing. So we would use negative 1. We would do this. Now, then it will be quadratic, so that'll be nice. We have a 2, a 1, a negative 4, a negative 3. Add straight down, multiply up. Add straight down, multiply up. Yay! So now we'll go over here. X equals negative 1 is the solution. So now from here, because we went from degree 3 down to quadratic, we're in heaven because we don't have to keep testing. So 2x squared minus x minus 3 equals 0. So now we'll solve by factoring. Now that we finally got it down to quadratic. Well, multiplies to be negative 6 and adds up to be negative 1. 3 times 2, negative 3. Long factoring. 2x squared. Negative 3 drop. And then breaking down my middle term as these two factors. So plus 2x minus 3x. So then from there we'll pull out a 2x, then left is x plus 1. Right here I'll pull out a negative 3, left is x plus 1. So now I can pull out x plus 1. It divides out and left is 2x minus 3. So my other solutions are x equals negative 1. So didn't we get this again? So multiplicity of 2, and we get x equals 3 halves, which makes sense because look, that was a possibility. So in this one, this degree 5 had all rational roots. Count. 1, 2, 3, 4, 5. So now we're going to use that to write it in its factored form. It says, use those roots to factor it completely. Okay, so guys, let's think about this. If x equals 1 is a solution, what would be a factor? X minus 1, right? Work backwards, guys. Subtract 1. Wouldn't x minus 1 be the factor if 1 is the solution? Okay. We would have a x plus 3. We would have a x plus 1 squared, and we will have a, okay, perfect. I like what she said, 2x minus 3. We need to write it like that. I always have people go x minus 3 halves, which is technically correct, but that's not the order we use to get it alone. So we wouldn't be times up by 2. Do you guys see how that would get rid of this 2? And then subtract 3. We need to write it like that. So it'll be 2x minus 3. That's factored now. So as you can see, it's not that it's hard, it's just a long process. Yeah. Forgot, because it did say, and then factor it completely. I think you get it now, don't you? How to work backwards now to write it in factored form. We would have an x minus 2, a 2x minus 1, and an x plus 3. And that would be the factored form of this. Okay, this one is a really good one to do because something kind of interesting happens here. So it says find the zeros, and it's really good that it happens honestly because it will help remind us of what the rational root theorem only gives us. So it says find the zeros of the polynomial and then graph it. So remember, zeros are where it crosses the x-axis. Do you agree? So we know for sure we have 4 solutions, but remember that doesn't mean that they have to cross. If we have imaginary solutions, they don't cross the x-axis. So let's go through and find the solutions. Well, we don't have a factoring technique to factor this, so we're going to have to use technique P over Q. So our Q is this, our P is this. Luckily, you guys, when Q is 1, your P over Qs are really nice and pretty. They're going to be whole numbers. So factors of P, everybody, plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. Are those the only factors of P? Yes. Any other factors of 10? No. Right? Now Q, factors of Q are plus or minus 1. Do you guys see why I'm not writing it? Because all of these divided by 1 are just all of those. Okay. So those are our possible P over Qs. So once again, we're going to have to just start testing. So I'll take 1. 1, negative 5, 23, 10. Not forgetting to check if there's anything missing. There's a lot to remember, I know. One doesn't work. Anyone find one that did work? Which one did you test? Well, then I can take a different one. You're doing 2? 2 doesn't work? Anyone else get something that didn't work? Or did? Yeah. Yeah, the remainder has to equal 0. Right. Because then it would have divided perfectly, which would make it a factor. Because my remainder wasn't 0. I didn't finish because I could see it wasn't going to be 0, so I didn't want to waste my time. Does that make sense? Yeah. So I guess I'll take 5. 5 works. Okay. 5. So let's see what we're looking at. We have 1, negative 5, 23, 10. Add straight down, multiply up. Add straight down, multiply up, add straight down, multiply up, add straight down, multiply up. Boom. Okay, so I'm going to make my bucket of solutions here. X equals, thank you for doing that, by the way, x equals 5. We know it's going to cross the x-axis at 5, for sure, or bounce. Because what if it's a multiplicity of 2? We're not going to know until we keep trying to solve. So what I would do from here, guys, is write down the new polynomial. So we went from degree 4 down to degree 3. That's x cubed. Then we have 0x squared, and then we have minus 5x minus 2 equals 0. Now, don't be mistaken. Don't look at this and say, well, that's like a quadratic. It's not a quadratic, though. You can't use quadratic form. You can't do factoring or quadratic form unless it's quadratic. You see how it's degree 3. Now, look, I always check, though. Is there a factoring technique I know to be able to use to continue? No, because there's not a greatest common factor. It's not U substitution. There's no way to factor this. So we have to keep testing P over Q. But we're going to make sure to use these coefficients. 1, 0, negative 5, negative 2 from this. Does that make sense? Because then we'll have it down to degree 2, right? So did anyone find another one that works? Are we sure that 2 and negative 2 don't work? Somebody try negative 2 by chance? This is going to take us all day unless we all start helping out. So negative 2 works. So negative 2, let's see here. So then we would have 1, 0, negative 5, negative 2, add straight down, multiply up, add straight down, multiply up, add straight down, multiply up, add straight down. Awesome. So now we'll go off and say x equals negative 2. Okay, so we're also crossing at negative 2. There's our other 0, or it could be bouncing once again, right? We don't know the multiplicities here. So now I'm going to write down my new quadratic, which is x squared minus 2x minus 1 equals 0. So now from here, we're going to see if it factors. Let's look. What multiplies to be negative 1 and adds up to be negative 2. People will sometimes say 1 and 1, negative, negative, but doesn't that multiply to be positive 1? So that doesn't factor. So to continue to solve, what would I need? Yeah, irrational or imaginary, right? And so if they come out to be imaginary, they won't cross the x-axis. But if they come out to be irrational, they cross the x-axis. They're just crossing at decimals that can't be written as fractions. Okay, so let's do quadratic formula. Because we have to graph, we have to know the other roots. So before, guys, do you guys understand we would have stopped at this point? Those are the only two rational roots. But this one says graph, so we got to keep going. X equals negative b plus or minus the square root of b squared minus 4 times the a times c. Do you need me to do something or like?
I just have a question. I saw you have the test earlier. Do you take it down already? I was just gonna rewrite it so I could have it for me next year.
Yeah, he took it down.
Thank you.
Yeah. Okay, so underneath our square root, let's see what we get. 4 plus 4. Do you see how it's gonna become plus 4? That would be the square root of 8. So just a reminder. How do we simplify that? Now, it's not imaginary, therefore they do cross the x-axis, just not at p over q places. So then we would break down square root of 8, 4 times 2, 2 times 2, so it's 2 root 2. So we have x equals 2 plus or minus 2 root 2 all over 2. So what would that become? X equals, they all become 1, don't they? So 1 plus or minus root 2. There's your other two solutions. X equals 1 plus or minus root 2. So everybody, we've got to actually, since those are real solutions, we've got to see where that crosses. So let's just type into our calculator. Decimals are easier to plot points on. So type in somebody 1 plus root 2, hit enter. Somebody do 1 minus root 2, hit enter. .4 is good. So, because I'm just doing a rough sketch here, right? So I'm going over 2 and then a little bit. And then what's the 1 minus root 2? Okay, so negative 0.4. So negative 0.4 roughly right there. Those are the places it's crossing the x-axis. Then what was the next step after you plotted your zeros when graphing? Graph the end behavior. It's even, it's positive. So it will be up and up. Therefore, I go to my furthest zero this way and I go up. Furthest zero that way, I go up, don't I? Now, do any of these have even multiplicity? They all have odd multiplicity since the zeros only happen one time. So it's going to cross through the zeros. So I start here, trace down, it crosses through. Isn't it going to roll, come back up, cross through? It's got to roll, come down, cross through, and cross through. There's our rough sketch. Yes? because they're different numbers. One plus root 2, one minus root 2. Does that make sense? Okay, any questions on that? Okay, learning another thing here, a new theorem. Okay, so Descartes' rule of signs. Start writing this down. So René Descartes is a mathematician clear back in the day before calculators and a long time ago when they had to do stuff by hand. So René Descartes, he's a guy, noticed a unique pattern. He started playing with polynomials in the sand or wherever he was drawing. I'm sure they had paper back then. And then he noticed a unique pattern with the roots, which means the solutions, right? With the roots, the zeros. He noticed a unique pattern with the roots and the signs of a polynomial. So he noticed this always works. So here's what happens, guys. Now I want to say this first so that you actually understand what I'm saying. Everybody look, here's an XY chart. Wouldn't all the zeros on this side be considered positive roots? Because they're on the positive x-axis. And wouldn't they be considered positive real roots? Because if they cross the x-axis, they must be real. Well, what René Descartes noticed is we will have at most the number of positive real roots as the number of sign changes between our consecutive terms. And then it goes down in twos. So let me show you. Look at this polynomial right here. What he noticed is that if we count the number of sign changes from one term to the next, from positive and negative, that will be the number of positive real roots every time. So let's see here. Positive to positive. Do you guys see how that did not change signs? That doesn't count. Positive to positive. It did not change. Still not count. Positive to negative. Do you guys see how it happened once? And then negative to negative doesn't count. We know for a fact that there will be one positive real root. It's going to for sure cross the x-axis over here one time. Does that make sense? Yep, and so it couldn't cross twice. So once we found, let's say we found x equals 2 was a solution, we wouldn't need to test 3 because it wouldn't cross at 3 because we know that there's only one of them. Does that make sense? So it's another way to kind of have it give us some useful information. It's not foolproof though. I'll explain in a second. Okay, so now how do we know how many times it crosses the negative x-axis? We just did positive. The original polynomial is testing positive real roots. Now, if we want to know how many times it crosses in the negative x-axis, the negative real roots, what we have to do is we have to take our function, we have to plug in negative x, which makes sense. Look, we're testing negative x's. We plug in negative x, and then we simplify it down, and it will be the same rule. We will have at most the number of sign changes between consecutive terms. So to test negative, I'll take the function f, plug in negative x, and simplify. So that'd be 3 negative x to the 6 plus 4 negative x. Isn't this the same idea of even, odd, or neither? It's the same thing we did, you recall. And then plus 3 times negative x to the 3rd minus negative x minus 3. Now I've got to simplify it. You guys don't mess up on simplifying something so simple here. And negative, don't say 3 gets multiplied in. That's not true. We have a negative to an even. Won't that become positive? Yes. So we have positive 3 times positive x to the 6. So that's 3x to the 6. Now right here we have a negative x to the 5th. A negative to an odd will be negative. Now look, that means we have positive 4 times negative x to the 5th. Minus 4x to the 5th. Now we have another odd, don't we? So it's a negative and a positive. So minus 3x cubed. And then a negative and a negative is a positive x minus 3. So now what we'll do is count. The same idea. How many times from one term to the next is there a sign change between positive and negative? Positive to negative, does not count. 1. Negative to negative doesn't count. Negative to positive, well, that's a sign change. 2. Positive to negative, 3. So there are 3, and it actually goes down in 2s. So 3 or 1, do you see how I subtracted 2, everyone? 3, that's always what you'll do. You'll take the highest, subtract 2. So 3 minus 2, there are 3 or 1 negative real roots. So one of the following is going to happen. It's going to cross one time in the negative x-axis or 3 times. Yes. Always. Until you can't go to negatives, though. That wouldn't make sense. You know what I mean? Because we're counting numbers here, so we can't go. There are negative number of roots. Does that make sense? Right. Well, no, yeah. So you'll just always start with the highest and then subtract 2, and then once you hit 0, you're done, or negative, you're done. So do you see how 3 minus 2 is 1? So like, what if I would have had 5? I'd say there are 5, 3, or 1 negative real roots. You see how I went down in 2. 5 minus 2 is 3, minus 2 is 1. It just goes down from the highest down. So what if there would have been, what if by chance there would have been 6 possible positive real roots? Let's go down, there's 6, but there also could be 4, but there also could be 0. So do you guys see how you just go down in 2s? That's going to happen. It's either going to cross 6 times, 4 times, 2 times, or 0 times. Now it actually makes sense if you think about it because, guys, imaginary roots come in pairs of 2. Irrational roots come in pairs of 2. So do you guys kind of see how we have to count in 2s? Because they're going to come in groups of 2s. These are real roots. Anyways, the imaginaries come in groups of 2. That's why there couldn't be without the down by 2 idea here. Yeah, so this is why, great point, everyone. Here is why it's not foolproof. People get this rule and then they think that these are rational roots. That's not true. The problem is, so Descartes' rule of signs, honestly, is just kind of something that helps us, but it's not foolproof. So x equals 2, it could be that, but also this is a real root. Do you guys see how these are both real roots? So this wouldn't be a possible rational root, but it still crosses the x-axis. So what happens is people will say, well, Ms. Christensen, Descartes' rule of signs says that it is crossing the positive x-axis, but I've tested all my positive rational roots, and none of them work. And I'm like, yeah, because remember, Descartes' rule of signs could also have irrational roots that cross. So just keep that in mind, it's not foolproof. Does that make sense, everyone? So it helps us more eliminate imaginary kind of. Okay, let's use it. Honestly, you guys, for the test, you're going to be asked it like this. So even if you didn't know how to use it to help you eliminate, like, which roots to test first, because honestly, it's another tool. You know how we had 10 million P over Qs? It's another tool to help you decide which ones to test first. But honestly, that takes just as long sometimes as just testing them all. So you just have to kind of memorize this and know it for the test, even if you never use it to actually use it. Does that make sense? Okay, let's do it. It says determine how many possible positive real roots and how many negative real roots the polynomial can have. Notice it does not say anything about Descartes' rule of signs, so that's something you'll have to memorize. Oh, I'm going to use Descartes' rule of signs and count to see how many changes of signs. So right now, let's find the positive. Remember, we're going to find how many times it crosses the positive x-axis. Ready? So don't we count? How many sign changes do you see? 0. So this is actually really helpful. There are 0 possible positive real roots. Now think about how this one actually would be useful. Do you guys see, we'll look at my P over Qs. We're going to have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. What can we eliminate? All the positives. You guys see how that is kind of useful. Okay, cool. Now let's test how many times it's going to cross the negative x-axis. So you'll have to know, okay, I plug in a negative x and simplify. So that would be negative x to the 4th plus negative x cubed plus negative x squared plus negative x plus 12. So simplifying, that would become x to the 4th minus x cubed plus x squared minus x plus 12. Let's count how many sign changes. 1, 2, 3, 4, right? So it's crossing 4 or 2 or 0, negative, real roots. So that's going to happen. It'll either cross 0 times, 2 times, or 4 times. But if we know for a fact, it will never cross anything different than that. Yes? So plus or minus 2i, right? If we think about the quadratic formula, don't imaginaries have to come in conjugate pairs? 2, right? So if it crosses the x-axis 1, 2, 3 times, and it's degree 4, if it's degree 4 and it crosses 3 times, could that even be possible? No, because then that would mean we only had one imaginary root, but they come in pairs of 2. So we have to go down in 2s. Yeah. So if there was 4, guys, if there was 4, that means there would be no imaginary, correct? If it crosses twice, how many imaginary would we have? 2, right? 2 imaginary. If it crosses twice, those are real. So, and then if we have 0, if it crosses 0 times, that means we have 4 imaginary, which makes sense because a group of imaginary, a group of imaginary. So that's why they go down in 2s, conjugate pairs of imaginaries. Okay, awesome. You guys are doing really good. Okay, so one more theorem. Another kind of hoop to jump through. It's actually useful, though, in a sense. Like you saw that, yeah, in that one instance, in that last example, Descartes' rule of signs would have helped us not test all those positive ones. Okay, it's called the upper and lower bounds theorem. So it says, okay, let me just explain, though, before I read the formula, what it's saying, because then maybe it will make sense to you. Guys, what this upper and lower bound theorem does is, if I have a polynomial and it's crossing, like, let's say I'm going to draw it, okay? Like, it's crossing here and here. What this lower bound theorem, we didn't know, let's say we didn't know where it crossed. What the upper and lower bound theorem gives us is an interval to tell us our zeros will fall between this interval and this interval. Like -7 and 8. Let's say that we know our zeros will cross the x-axis between -7 and 8. It just gives us an interval, so like between which all your zeros will cross. So we can know for a fact that it's not going to cross at 9. Because it's on an interval from 8 to -7. It's crossing in there somewhere. Does that make sense, everyone? Okay, so like I said, let P be a polynomial with real coefficients. So that means we're not going to have imaginary coefficients, which makes sense. If we divide P of x by B using synthetic division, and the coefficients are all positive, then B is considered an upper bound for the real zeros of P. So we'll do that again. So looking at this right here, it says show all the real zeros of the polynomial lie between -3 and 2. So do you guys see how 2 would be our upper bound? What this theorem says is if you do synthetic division with B, or 2 is B. If we do synthetic division with 2, let's do it. The theorem says if we do synthetic division with 2, let's do it real quick. Add straight down, multiply up, add straight down. Did I miss something?
Yeah.
What?
That's huge.
Ah, see, I knew something. You gotta be careful. My bad. So 1, then 0, then -3, then 2, then -5. Add straight down, multiply up, 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 add straight down. So all we have to look at now is the signs on those coefficients. It says if these coefficients, it says if the coefficients are all positive, then B would be considered an upper bound. So we know because all of these are positive that 2 is an upper bound. So you're showing, it says show. So then you'd say all positive. So it's something you have to memorize, you know? So what if it would have been positive, positive, negative, positive, positive? We would say it's not an upper bound. 2 is not an upper bound. So we need to go further out, like 3. Yes. Once again, the interval that your zeros are falling between. So our zeros are going to be between 2 and -3. It's going to cross the x-axis between 2 and -3. So could it cross at 3?
And so we know that it is if they're all positive.
Right.
It's all around it.
Right. So you see how it just gives us an interval, like your zeros will cross in here, inside this window, for sure. They're going to give you the interval. See how they gave you the interval? We're just proving it. We're showing it. So let's say they didn't give it to you. You'd have to guess and check. Yes. Okay, now let's read the second part. I haven't read second part 2 yet. Okay, so now testing lower bound. So if we take p of x and divide it by a, so from a to b, our interval from a to b, so if we divide p of x by a using synthetic division and the coefficients alternate, so lower bound they have to alternate between positive and negative, then a is considered a lower bound for the real zeros of p. So what happens with an upper bound? They all need to be positive. What happens with a lower bound? They need to bounce, alternate. So let's test, is negative 3 a lower bound? So we'll do negative 3. Coefficients 1, 0, negative 3, 2, negative 5. So add straight down, multiply up. Add straight down, multiply up. Add straight down, multiply up. Have I messed up anywhere? Multiply up. $48 positive. Add straight down and we get 43. Okay, let's check. Is it bouncing between positive, negative, positive, negative, positive? Yes. So then it would be considered a lower bound. So you'd say alternating positives and negatives. So we've now shown upper bound, lower bound. So guys, this polynomial, let me show you. Well, it doesn't, these aren't the zeros. That's just the interval. So here's negative 3. Here's 2. It is only going to cross in here somewhere. So then that would help you eliminate. Could it cross at 5? You guys see how that helps you eliminate p over q would have a 5. Then you wouldn't test 5. Yes.
And so will the always do this numbers to find
There'll be a part on the test where they do, yes. I don't know for sure though if they'll make you do it on your own, but I'll give you an idea of where to start if you weren't given it. Okay, let's do it again. How about, you guys want to try it by yourself, this one real quick? Okay, try this one by yourself. Show that the given values for a and b are lower and upper bounds for the real zeros of the polynomial. So that's how I would just show my work. Remember, these aren't zeros, this is just an interval that shows you the zeros will be between this and this, but that doesn't mean it's going to fall on that. Doesn't mean that's a zero. Does that make sense? So there's an interval. Yeah, exactly. We're just looking at the sign. And this is not necessarily a zero, everybody, once again. That just means that it could cross at negative 2. It could cross at negative 2.7. You guys see what I'm saying? It could cross at negative 3, but it doesn't necessarily have to, yes.
So is it like the lower bound, like how much farther down?
I would just go down in whole numbers.
Okay.
Now keep in mind, there are going to be multiple correct answers for upper and lower bound. Because what if is negative 3 a lower bound? Yes, correct? Now guess what? What if I would have tested negative 4? It'll also be considered a lower bound. Because it helps us get closer and closer. Does that make sense? So if I test negative 2, it would be no. So you'd say, okay, it's from negative, does that make sense? But further out would work too. It's just like basically you can close in your interval and get smaller and smaller, and then you're like, boom, that's where I gotta stop. Yeah. Yes, I don't think it can be negative positive. I think it needs to start positive negative. Right. Right, every time. Great questions. Okay, awesome. Okay. Oh. Okay, so here's how I would start, everybody. So it says on the homework, this is almost my last, I think this might be my last example. So it says, find integers that are upper and lower bounds for the real zeros of the polynomial. Here's where I'd start. I'd find the possible rational roots, and then I would start with the highest and lowest rational root. But that doesn't necessarily mean that they're going to work. That just gives me a starting point. So I'm going to say, here's my Q, here's my P. So factors of P plus or minus 1, plus or minus 2, plus or minus 4. Factors of Q plus or minus 1. So P over Q plus or minus 1, plus or minus 2, plus or minus 4. So now it could cross at -1, -2, oh, sorry. It could cross at, I'm going to go in order, -4, it could cross at -2, it could cross at -1, yeah? Putting all my negatives in order, so I'm used to write it. It could cross at 1, 2, or 4. So which two values would I choose to be a lower and upper bound? -4 and 4. Now, that doesn't mean they're necessarily going to work. Like, what if -4 doesn't work? Then I would try -5. Go further out. Because remember, intervals don't have to have the zeros. They don't have to contain the zeros. It's just on an interval from here to here. All right, so let's, because couldn't it cross past this if it was irrational? Okay, so I would say -4, do my synthetic division, go through. If they're all positive, we'd say yes. So there's going to be multiple correct answers for this. Now, how would this be useful? The next thing you could test is -2. And then if -2 works, do you see how you can eliminate -4 as an answer? Because it's closer in. The interval is actually closer in. Does that kind of make sense? So it just is kind of useful. Do you want me to keep going, or do you guys get it? Keep going? Okay, so testing -4, what should I put in? 1, -3, 0, 4. Add straight down, multiply up, add straight down. Multiply up, add straight down, multiply up. It's going to be negative, and it doesn't even matter. Look, won't that come out to be negative when I add straight down? Positive, negative, positive, negative. Did that work for my lower bound? I just put negative number because I didn't want to calculate it because it doesn't matter what the number is. Do you guys see what I'm saying? So it is a lower bound. Does that mean it's definitely going to cross at -4? No, that just means that's like it is on that interval. -4, it won't be -5. Does that, or -5 something or whatever. So you'd say A is my lower bound, so -4. Now, once again, what if you want to actually use this? The next thing I test is -2. Because once again, if -2 works, then we're good. Because there could be multiple lower bounds. It's just pulling in the interval. I would. That's where I start. What if that wouldn't have worked? I would have had to go further out. Does that make sense? Okay. No. It's just like I'm showing you how it would be used, actually. Because right now we haven't used it for anything. So then upper bound would be 4. Do synthetic division with 4. So 1, -3, 0, 4. And then if they all come out positive, 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 it's an upper bound. So then your B value is your upper bound. 4 would be an upper bound. So your zeros would all cross between -4 and 4. So that's kind of a big interval. It's kind of nicer if you're going to actually use it than to make your interval a little bit, try to see if it can be smaller. I think you could even just say lower, upper. Yeah. Yes.
Are there gonna be questions that have to do like all of like finding the interval and that?
Well, yeah, but that won't change anything, right? The interval just tells us where the zeros are, but if we have to graph it, we have to find the zeros anyways, so I don't really think that they would put that together, if that makes sense. Okay, it says right here, show that the polynomial has no rational roots. How would you do it? I won't go through it if you can tell me how you'd do it. It tells us there are no rational roots. How would we show? P over Q, and then what would we do with all the P over Qs? Test them, and what do we know the remainder is going to be not? 0. Do you guys see what I'm saying? So it says show that this has no rational roots. You just test all the P over Qs and say no remainder was 0. Yeah, but look, there's not going to be very many. 2 and 2.
I was like,
So there'll be like 4 if they ever ask it like that. Okay, so do you guys need me to give another example of finding, like doing the P over Q, solving it completely, or do you guys feel good with using P over Q? Okay. Awesome. Okay, that is the end. Let's see if you can practice some.